Good evening. It's a real pleasure for me to sort of open this Planck meeting, and to talk to you. And so I'm going to talk to you about attosecond light pulses, very short light pulses, and I also would like to put this in the context of this International Year of Quantum Science and Technology. I start by simply telling you what is this time scale, attosecond. Attosecond is 1 billion of a billion of a second, 10 to minus 18 seconds. And here, this is called the era of time, going from the age of the universe, which is approximately 10 to 18 seconds, down to attosecond. And you have some time scale for humanity, astronomical time scales, the second, this is the heartbeat, and then my time for mechanics, time for electronics, time for motion of atoms and molecules, and attosecond is the time for motion of electrons in atoms. So in general, the lighter the particles, the faster they move. To capture atomic motion when it's femtosecond pulses. And this led to a Nobel Prize in Chemistry to Ahmed Zeewar for the field of femtochemistry. And then to capture the electron motion, we need attosecond light pulses. And this was awarded a Nobel Prize in 2023 to Pierre Agostini, Ferencváros, and myself. And this is the story of this Nobel Prize that I want to tell you tonight. So this is the outline of this talk. I will tell you about the background to this research. Then I'm going to tell you about high-order harmonic generation, attosecond light pulses, and finally a little bit of attosecond physics, what we do with this attosecond pulses. So the background of this field of research is first of all the laser. Without the invention of the laser in 1960, we would not have done this. So this is a picture of one of the first lasers, a ruby laser, which was invented by Theodor Maiman. And you know that the laser is due to light amplification by stimulated emission, which was discovered theoretically by Albert Einstein, 1916, following the discovery of light quantum, photon, by Max Planck. I couldn't let me to put Planck in this talk. I hope that you like it. 1900, so we actually started this quantum revolution. Okay, the invention of the laser opened new fields of physics. One of them is called nonlinear optics, and here you have the first nonlinear optics experiment performed already in 1961 by Peter Franken. So what you see here is a laser, first laser, ruby laser, which is focused by a lens into a piece of quartz. Then the radiation is analyzed by a prism. And then you have a detector. In this case, long time ago, it was simply a photographic plate. And on this detector, you observe first the laser light, frequency nu, and then a second harmonic of this light, frequency 2 nu. So you have creation of new frequencies through this phenomenon, second harmonic generation. You can represent it this way. You start from the fundamental here, absorption of 2 photons and emission of 1 big photon at frequency 2 omega. Another field of research which was open due to the invention of the laser is atoms in strong laser field or multi-photon processes. This is a simple two-photon excitation. So an atom is excited to an excited state by absorption of two photons. These processes have actually been predicted theoretically by a great physicist, woman physicist, Maria Goeppert-Mayer in 1931. If your laser is intense enough, you can also have multi-photon ionization, where the atom absorbs enough photon to get ionized. And this was actually pioneered by Russian scientists in the 60s. In 1979, Agostini and co-workers discovered the phenomenon of above-threshold ionization, where an atom can absorb more photons than what is strictly needed for the ionization. For example, here, one more photon. And you can observe this process by looking, if you look at the ions, you don't get the information. So you need to look at the electrons. You would detect an electron with this energy and then another one with this energy. You need to do electron spectroscopy. My own thesis work, a long time ago, in the 80s, was to look at multiple ionization processes by multi-photon absorption, or by exposing these atoms to strong laser fields. Here you see a double ionization of xenon atoms by absorbing many photons. So at that point, it was becoming clear that it was possible to really excite, ionize atoms by absorbing photons. And if you have excited atoms or excited ions, it would be interesting to look at the fluorescence from this excited species. So this is what we set up to do. Now I'm going to the second part of this talk, high-order harmonic generation. So we set up an experiment. At that time, I was a young researcher in the same institute where I had done my thesis work, called Commissariat à l'énergie atomique in France, in Saclay, close to Paris. So we set up an experiment where a little bit looking like the first experiment I presented to you about second harmonic generation, but instead of having a piece of quartz, we have a gas of atoms. We have a small gas jet, and we use rare gas atoms. And then we have a grating, and then a detector. So this was the experiment. Again, the aim was to look at the fluorescence emitted by atoms exposed to a strong laser field. We did not see fluorescence. Instead, we saw high-order harmonic generation. So this is the beauty of experimental physics. Sometimes you see an unexpected process, and it's extremely exciting. And this is really, I think, the reason why I'm here today, why I was awarded the Nobel Prize for this experiment, and then the development that has followed. So here is one of the first high-order harmonic generation spectrum. So you see here intensity of light that is detected as a function of wavelengths, and you see peaks, quite narrow peaks. This is obtained in the gas of argon. The peaks correspond, I mean, the frequency of the light is a multiple, indicated by this number, of the laser frequency. If you plot the intensities of these harmonics as a function of order, you find this behavior here with a decrease for the first orders, and then a plateau, and then a cutoff. this plateau behavior was really the surprise, because we thought that it would be more and more difficult to generate harmonics with higher and higher order, so that the intensities of this harmonic should really decrease. And this is not what we were seeing. We were seeing this plateau behavior. You can see that we only observe odd order harmonics. This is due to the symmetry of the interaction, symmetry relative to the origin. I'm not going to explain it in more detail, so believe me here. If I say what I said a little bit more mathematically, why this plateau was a surprise, this is because at the time we were thinking very much in terms of perturbation theory for the interaction between light and the atoms, where you get a polarization in the medium due to the laser as a series of powers of the electric field of the laser, and for such a series not to diverge, you need the first order to be much larger than the third, much larger than the fifth, etc. And this was obviously not the case, since the intensity of all of these harmonics is about constant. Where are we in the electromagnetic spectrum? This is a picture of the electromagnetic spectrum from radio waves. You have the visible part here, which is very, very small, as you know, ultraviolet, X-rays. This area is called extreme ultraviolet, below X-rays and above ultraviolet. So we start with a frequency nu in the infrared region. This is the wavelength of the light, or the frequency of the laser light that we use. And then we multiply by a high integer. We arrive, for example, here, 31st harmonic. We arrive in this extreme ultraviolet part of the spectrum. This radiation is invisible to eye, and actually strongly absorbed by matter. So we do these experiments in vacuum. If some of you are already lost in what I'm saying, let me do a little analogy between music and the physics that we are doing. If you play some music instrument, for example violin, you play a certain tone, you will get not only this tone, but many harmonics. And these harmonics actually, the number of harmonics that you get give the clang of a music instrument. So in both situations here, what you have is a strong interaction. Here between atoms and the laser, and here between the string of the violin and the bow, leading not only to a certain frequency, but frequency plus a number of harmonics. Of course, these are acoustic waves, and here these are light waves, so very different type of waves, different frequency regime. We are talking about coherent light. Laser-like light is not incoherent light emission, as is everywhere when you look at light around you, lamps, sun. It's something like that. This represents atoms being excited, and then with emitting waves in any direction at any time. Here we have a real coherent light emission where atoms emit in one direction and also together. You need to have a certain phase matching condition here. These waves need to be in phase in order to build up a harmonic process. Here as well you can make a small not completely rigorous, but music analogy with an orchestra. Your ensemble of atoms are the musicians. And this situation is what you can listen before the concert has started. You know what I mean? And here, when the concert starts, the musicians play together, and you get this coherent light. If I want to formulate a little bit more physically what we're talking about, and this is something that I like very much as young researcher in this field, you need to put together two physics domains. One is quantum mechanics, how to describe the interaction between one atom and the laser. We need to solve the Schrödinger equation as written here. With in this number you have of course the atomic potential and the laser atom interaction, which is here described with classical electric field, electromagnetic field, time dependent. This is your laser field. And this is interaction described in the so-called dipole approximation. But you also need to consider the many atom response, what happens in the macroscopic medium when you have this interaction. Again, you need all these waves to add coherently. And this is part of electromagnetism described by Maxwell's equations, which in this case can be simplified to a wave equation as is written here, when you describe here the generation and propagation of a harmonic field due to the medium polarization, which is coming from the solution of the Schrödinger equation. So you need to really consider both aspects in order to describe theoretically the problem. And actually the first attempts to understand the experimental results were to solve numerically both the Schrödinger equation and a wave equation, which work quite well. At the same time, simulating does not really tell you what is the physics behind. So now, this was the discovery of high-order harmonic generation. We studied this process, and we built, so now we are in 1992, we built dedicated instrumentation to study these processes, and this is a photo of an instrument that we built. So I was a young researcher here. This is me, yeah? And this is my first PhD student, Philippe Balcourt. So we built this instrument that you see here. What is below here are vacuum pumps. As I said, we need to be in a vacuum. You don't see the laser, it's coming from behind the wall here, there is a hole. What you see here is a gas jet, so the gas is coming from this small tube. And then you have vacuum chamber here. In this chamber, for example, you have optics, in this case a toroidal mirror and a grating to analyze the radiation. It's more or less the same components as I have described already. And then we have a photon detector, which in this case is an electron multiplier. 92 is also the time where there is a huge progress in laser technology and a new technique called jumper amplification that was discovered by Thomas Strickland and Gérard Mourou, and they were awarded the Nobel Prize in Physics for their method of generating high-intensity, ultra-short optical pulses. So it's a method to actually amplify short pulses without damaging the laser material. And in Lund, in Sweden, this is south of Sweden, physicists decided to combine this new technique together with a new laser material called titanium sapphire. It's sapphire with titanium ion. You can see it here. It's producing orange light. And so they create a new facility at the Lund Laser Center. And they asked me and my PhD student to come and try to study this, at the time, new phenomena of high-order harmonic generation with their laser. And it was actually fantastic to be able to use this new laser. We could study this process with much better condition. So this was in '92. What happened is that I met also my future husband in this collaboration, and 2 years later I actually moved to Lund and became associate professor in '95 and professor in '97. I'm coming to the third part of this talk. Are you following me? Yes? Which is attosecond light pulses. So attosecond light pulse is an idea that was raised maybe a couple of years after the discovery of the high-order harmonics. And the idea is presented in this cartoon. So here you have 3 harmonics, 17, 19, and 21. So these are waves with slightly different frequencies, so the number of maxima is increasing. So now let's assume that these 3 harmonics are phase-locked. That means with the same phase at a certain time, you have here the 3 maxima which coincide. Because of the periodicity of the process, after half a laser period, you will have the minima at the same time, in phase, and again the maxima and the minima, etc. So now let's sum these 3 waves. You can do that in your head, right? What do you get? So I do a sum. I get a series, we call this a train of short light pulses. And the reason is due to interferences. In this region here, where these harmonics are in phase, you have constructive interferences. So you have a lot of light. While in the middle here, where the maxima and minima do not are not at the same time, you have destructive interferences, and then again constructive, destructive, etc. So the light is confined into small time intervals. You get short pulses. And the period, the half period of the laser that we have been mostly using, titanium sapphire, is 1.3 femtosecond. So you see that now you get into the attosecond regime, a few hundred of attosecond. So this is a representation of the intensity of these pulses. And now if you sum not only 3 harmonics, but 10 harmonics, what will you get?
Little pulse.
See, you need to speak louder so I can hear.
A single pulse.
Yes, I think I heard you get, of course, larger amplitude, but especially you can get even shorter pulses. This is an expression of Heisenberg principle. If you have a large bandwidth, many harmonics, you can get, you don't get necessarily, but you can get shorter pulses. So this sounded very, very interesting. The reason for this possibility to have short pulse. First of all, is you have a high frequency of the light. We are in the extreme ultraviolet, so we have a high frequency here. We have a short period of light, so you can get light pulses with a few cycles in the light, a few periods, since this period is short. You have a broad bandwidth because of all these harmonics. The big question was, are the harmonics phase-locked? Is this assumption that they are all in phase, is it true or not? And actually it's going to take us 14 years to really be able to answer to the question, do we have attosecond pulse? And myself, at least at the beginning, I was a bit skeptical. Huge progress in theoretical understanding in '93 with a model, a very intuitive model called the three-step model, which is presented here. So what you see here is the atomic potential, which is distorted by the laser. So normally it's Coulomb potential is like this, with a revolution symmetry. You with me? Yeah. And now, because of the laser-atom interaction, it's bent in one direction, and this is, of course, moving in time with the laser field like this. Yes, you still with me? So that means that at a certain time, the electron here in the ground state can tunnel through this finite barrier because of the laser field. So this is quantum tunneling. Then the electron is driven away by the laser over a few nanometers, so it's much more than the size of the atom. And then the electron is being driven back when the laser changes of sign. And then there is a probability for recombination back to the ground state. And in this process, you have emission of high energy photons. Let me say that this three-step model, which was kind of intuitive, semi-classical, you mix up a little bit of quantum process here, classical motion of the electron in the field, and then you have a recombination, which is again a quantum process, was formalized and generalized very, very nicely by Maciek Levenstein, who is actually in Barcelona, so it's a pleasure to acknowledge his contribution to the field that was really huge. And I had the pleasure to work with him during many years in the 90s. And what he did is formulated a theory called strong field approximation that still has a very strong impact in our field. Now, this maybe was a bit hard, I don't know. So I have a little analogy, which is called the adventure of an electron in a laser field. So here we have an electron bound to the atom, strongly bound. It's good, otherwise we would not exist. This is not a spelling mistake, it's in Swedish. So I'm teaching a little bit of Swedish at the same time. It's very easy, you replace C by K. You can represent this like this. This is an electron in a prism, and on the side you have a roller coaster. I don't know if you have this in Barcelona. Do you have that? Yeah? So the electron would like to have fun. What does the electron do? No, you need to speak a bit louder here. I want to hear the right answer. You are going to do a competition tomorrow. So come on. Yeah, I get the right answer almost immediately. Yes, that's the right answer. Great. This is called, because usually people, I present this, but it takes a long time to get the answer. People say the electron does this, or the prison collapse, or something like this, but of course this is the solution. So I see directly that you are right students. Okay. Life is good. The electron has really fun. Is being accelerated and then decelerated in the laser field. The story is finishing very bad. You're laughing, but it's not fun. The electron is meeting his prison, which is open, and falls, and it's screaming its energy. This is the analogy of the light pulse. This is end of the story. Okay, going back to this picture that is starting to be clear with this electron motion leading to emission of short light pulse. You see that we start to understand actually this phenomenon, this interaction between light and matter in the time domain. We started to study in the frequency domain, we saw these harmonics, but actually we describe it in the time domain with a repeated emission of short light pulse every half laser period. So you have this motion, and now here it's on the other side of the atom, and again and again. Now if you go from the time domain to the frequency domain, Fourier transform, you recover your spectrum of high order harmonic generation with odd order harmonics. And the fact that it's odd order is actually related to, now I'm coming a little bit to this symmetry property I mentioned before, is due to the change of sign of this between consecutive attosecond pulses. This is actually very similar to another very famous physical phenomena. Can you guess? Have you seen something like this before? This is my second question to you. Preparation to the competition tomorrow. If you think about this is time and frequency. If you replace, now I'm going to help you, time and frequency with space and space, what do you say? Diffraction through multiple slits. These are our slits, but they are not in space, they are in time. But it's very similar, and mathematically it's actually very, very close. Okay? I want to say I have one slide on the second aspect of this phenomena, which is the macroscopic part, which we call phase matching, propagation in the nonlinear medium. So for this to happen, that you have a coherent build-up of the harmonics, that they stay in phase, you need the phase velocity of the fundamental to be equal to the phase velocity of the harmonic field which are generated. I guess you understand, yes? So you need the refractive indices. Now I'm doing a little bit of optics. You need the refractive indices of the two fields to be equal. So is it possible? Well, let's look at the variation of the refractive index as a function of frequency over a large range. It looks like this, roughly. So in the visible region, or near infrared, where we have our laser, the refractive index is larger than 1, while in this region where harmonics are generated, the ultraviolet vacuum, extreme ultraviolet, it's less than 1. So if you look at this, the answer is no. Phase matching is not possible. The two light the light generating the harmonics, and the harmonics do not propagate at the same phase velocity. Fortunately, in this process, which I described, we also ionize the medium. So some of the electrons that I showed, remember this adventure of the electron, actually some of the electrons escape the prism. They get ionized. They become free. Well, the atom really is ionized, so the trajectory, instead of coming back and recombine, is moving like this. So you get some free electron in the medium, which you add the term here in the expansion of the refractive index at the fundamental frequency, and it becomes less than 1. So you can achieve phase matching with a degree of ionization of the order of a few percent. If you ionize too many atoms in your medium, then it will be even lower, and you re-in phase matching. So there is a certain window of laser intensity where this process works, where you have a strong laser atom interaction, emission of all these harmonics, and in addition they are phase matched. It's a little bit, in addition, influence of the focusing geometry, but this is a little bit for more advanced description of this. Okay, I'm coming to the next step, which happened in 2001. And this was the really first measure of attosecond pulses, both in a train and isolated pulse. And this really led to Nobel Prize of my two colleagues, Pierre Agostini and Ferenc Ross. And this was very important. Until 2001, we understood that maybe in some condition we could have attosecond light pulse. We were starting to really understand the physics, but still you need the experimental confirmation that yes, this was possible. So I would like to describe in some detail the experiment by Pierre Agostini. So this slide is a little bit more advanced. I hope you follow me so far. Yeah? So this one is maybe a little bit more advanced. So the process that Pierre Agostini and co-worker used is called two-photon ionization. And so what they use is the ionization of a gas by absorption of a harmonic in blue plus a laser in red. And of course they detect this by looking at the energy of the electrons. So we're not looking at light anymore. I'm going to show you an experimental setup in a moment. We are looking at electrons. We generate light, we transport light into a new chamber where we have a gas, we ionize a gas, and we look at electrons. We're going to focus on this sideband peak here. This can be reached by another process, which is now absorption of the next harmonic, and then stimulated emission, a little bit of laser here, of a laser photon. So now you see that we have two processes leading to the same final state, the sideband, this process and this process. We are in quantum mechanics. We make a superposition of two quantum paths. We add the amplitude of these processes. This technique is called rabbit, which means reconstruction of attosecond beating by interference of two-photon transition. So when you add the amplitudes of these two processes, the way you add this amplitude is going to depend on the phases of the two quantum paths. So in this path, you have an influence of the phase of this harmonic. In this one, the influence of the phase of the next harmonic. Then there is a delay between the harmonics and the laser. So you have a phase contribution equal to omega tau. Omega is the laser frequency, and tau is the delay. And on this side you have minus omega tau because it's an emission process. So the signal, the interference signal that you have here, can be written as this equation with a cosine term. And here you have the phase difference between the two quantum paths, omega tau plus phi q minus omega tau minus phi q plus 2. And you see that if you vary the delay here, you are going to have an interference signal that depends on this phase difference here. And this is what I want to know. I want to know if the harmonics are synchronized. So I need to measure the difference of phase between consecutive harmonics. Let me show you how we can do such an experiment. You need two parts. One is called Attosecond interferometry. So here I am splitting the laser into two. One path here is called the pump arm, where I generate harmonics here in the gas cell or gas jet. So I generate Attosecond pulse train, and then I remove the fundamental field here, co-propagating with a metallic filter. So I get here a train of Attosecond pulses. And then I have a probe arm with a delay stage, and I recombine the two here. So what I get is a superposition of the pulse train and this laser with a variable delay. This is the size, this is called a Mach-Zehnder interferometer, and the size of it is roughly 1 meter times 2 meters, this size. It needs to be very accurate. We talk about accuracy of 10 nanometer in space, few tenths of attosecond. The second part is electron spectroscopy. As I told you, we need to detect electron, the energy of the electron. So here we put some gas. We focus with a mirror here, with two radiation, and we detect the energy of the electrons. This is what we get. This is called a rabbit spectrogram. So what is shown in color is the electron spectrum, and it presents some peaks. You have what is called main bands due to absorption of harmonics. And then in the middle, you have these side bands separated by twice the laser frequency, and you see that they are nicely oscillating. And the information that we are looking for is really, where are these oscillations? Are they the same between sidebands, which would mean that the harmonics would be perfectly synchronized? You see immediately here that they are not exactly synchronized. So this is here now the periodicity of the process, again, is half a laser period. So Agostini did this measurement. He saw phase difference that were not exactly equal to 0, that vary a little bit, but in a way which was nice, and using this information plus the intensity of the harmonic, he could recover pulse duration of 250 attoseconds. So this was the first experimental demonstration of these pulses. I'm not going to describe the method used by Plancks. Plancks used very, very short light pulses to begin with in order to have essentially 1 attosecond pulse, and could measure them with the help of a technique called streaking technique. But it's similar in a way that it's use a delay between laser and the XUV radiation, and also measuring the kinetic energy of the electron. And on this result, the pulse duration of the attosecond pulse is 250 attoseconds. Today, the record is about 43 attoseconds. I'm coming to the last part. Are you still okay? Yes? A little bit of attosecond physics. What do we do with these pulses? First, I want to show you how it looks like. What is a lab in this field of research? It's a small lab, and it's like this, not like this room, but like this you see here. This is an example of laser that we use. These are not simple small laser like this one, but kind of advanced laser technology, but not huge. It's a lot of fun to work with laser and optics. Now I'm trying to recruit people here. And here you have vacuum chambers that we use where we generate this light and use them for application. What are we trying to do? We're trying to follow electron in atoms and molecules. What does it mean? First of all, let's look at Bohr's atom model, 1913, where he proposed a kind of planetary atom with atoms moving around the nucleus, like the Earth is moving around the Sun, but on quantized orbits. If you look at the time for an electron on the first orbit to make a full rotation, it's 150 attoseconds. So you see that we are in the right time scale. However, you know that quantum mechanics tell you that these are stationary state, and the electron can be anywhere in some area of space, decided by the wave function square. So this we really cannot do. One thing we can do is really look at electron transition, like photoionization, like the photoelectric effect, which was actually discovered in 1887 by Heinrich Hertz and explained theoretically by Albert Einstein. So Einstein I show actually twice in this talk. So I didn't manage to get Planck another time, but it's still here. So this is an expression of the kinetic energy of the electron, which when the atom is ionized by absorption of radiation with sufficiently high energy, you get h nu. Again, the photon energy minus the ionization potential of the atom. So what we can do, and this is new, we can really measure the time it takes for electron to propagate out of the potential. This is in this sense that we are watching electrons move. We are not doing anything in space, so we are not making a photo of the electron. There's no way we can do that, but we are measuring time. A little bit the same way to say the same thing, but looking again at this photoelectric effect, Einstein really focused on how to describe light, to explain the observation and the kinetic energy of the electron. Really, it was very important because it really led to the concept that light is both particles, photons, and wave, but probably he was thinking of the photoelectron as a particle going away and coming to a left-hand click. You can measure its energy or its momentum. The person that really say, oh, but if light is both particle and wave, then maybe matter, in particular the electron, can also be both wave and particle. Was Louis de Broglie in 1924, and this really led to quantum mechanics in 1925 with the Schrödinger equation and the Heisenberg representation of the same equation. So the question we ask, and actually what we can observe with our technique, is what are the wave properties of the photoelectron? It is also a wave. So it has an amplitude and a phase. Can we measure this phase? A little bit. Another question, what are the quantum properties of a photoelectron? So let's start by this one. And I'm going to take an example, a simple example, which is photoionization of helium atom. Simple atom. Close to a resonance. So I'm looking at photoionization of helium by absorption of 60 eV electron, 60 eV photon, sorry. So we create a wave packet here. This blue thing here is a kind of electron wave packet representation. But now we create this close to an excited state, doubly excited state, 2s2p, and there is an interaction here, a Coulomb interaction, so that if you have photoexcitation of helium atom, then you can have a autoionization process leading to ionization. So helium atom can be ionized by two ways, two quantum paths leading to the same final states. You recognize the story. Either directly or via this excited state. So EN, it's a quantum interference effect, quantum superposition of two waves. How do we look at this photoelectron? Similar to how we measure attosecond pulses, we use a quantum interferometer. We use another harmonic here, absorption of laser photon or emission of the laser photon. So what we do is we make a copy of this electron wave packet, a little bit below in energy, and we read the phase here and the amplitude of the signal by interferometry. Same experimental technique. What do we see? We see a beautiful interference signal. This is the amplitude and this is the phase. And you see that there is a nice interference signal due to interference of these two quantum paths and a phase jump of pi. Now what is very nice is we have the information, both phase and amplitude. You can make a Fourier transform and go to the time domain and really look at the time evolution of this electron wave packet. You can even do better. You can make a time frequency representation of the photoionization process. And here you have a representation of time frequency representation, which is actually a Wigner representation, showing the evolution of the wave packet in time. So you see that first you have a yellow thing here. This is direct photoionization, which happens over large bandwidths and short region of time. Then you have a region here, few femtosecond, where you have strong interference. This is where both paths are equivalent and strongly interfere. And then you have mostly the photoexcitation process, which is lower in energy and happens over a short time, a longer time. So we finish by a little bit the research that we are doing. So this is a little bit more advanced, and I won't say very much. Can we do better than that? Here we assume that this photoelectron is fully coherent wave. Is it always the case? The answer is no. Sometimes it's not fully coherent. So really to characterize the state of this photoelectron, you need to measure its quantum state. So let's look here at argon. So the technique that we do to actually measure the density matrix of the photoelectron is again based on interferences, but this time using two different colors. And just to explain the interferometer concept here, I'm going to split this photon into two. I'm representing two different frequency components of the same light. You see that now I can reach the final state here by two quantum paths, same story. I vary the delay between these photons and these ones, and I measure a signal. Now it depends on the difference between the two frequencies here. But now you see that the interference signal here is going to depend on whether these two positions here have a certain phase relationship. If there is no phase relationship because of decoherence, then you won't see any interference signal. In other words, what you measure here allows you to measure the coherences of the photoelectron. And we can retrieve a density matrix. So this is energy, this is a diagonal, and what you see here is that this density matrix is actually oval, which means that, well, it's not a pure state, it's a mixed state. So what is the reason for that? The reason is actually called quantum entanglement. When you ionize argon atoms, argon ion can be left into different states. So you create the wave function of your system is you have an entanglement between ion in two different states and the electron. And since we're not measuring the ion degree of freedom, we only measure the photoelectron, we lose coherences in this region. So I showed that just to tell you a little bit one of the directions of these fields. So I'm now coming to the conclusion of this talk. This field is really opening up into many directions, into molecular physics, condensed matter physics, into quantum physics, a little bit application to industry. So I hope that at least some of you will do Attosecond physics if you do a master project or thesis. So with that, I would like to thank my research group that you see here in Lund, photo taken quite recently. And I would like to wish you all good luck with your competition tomorrow. Thank you.